All right, welcome back. This is a longer section than the previous two. So thanks for bearing with me. And example 6 is not going to be that bad. And it's kind of fun because now we're going into the third dimension. We have our three vectors. So we're going to graph the span of u and v here. So the traditional way to draw the R3 coordinate axes is like so, where you have your x, y, and z, but we're calling it x1, x2, and x3 axes. And let's start with just the vectors u and v. So with u, we're coming out like 1 unit in the x1 direction, and then from there going 3 units in the x2 direction. So that gives us a vector about here. And v just means we're going 2 units in the x3 direction and not moving in the x1 or x2 directions at all. So that looks like this vector here. So that's u and v. But to graph the span of u and v, that means the set of all linear combinations of them. So that includes u plus v, which is about here. So just connecting tip to tail, like so. It includes negative v. It includes negative 2v, positive 2v, negative u, negative u plus 2v, and so on. It also includes vectors like 2v plus 1.5u. So if you do 2v plus half of u, you'll get something like this. And all these other points, any multiple of u plus any multiple of v, they end up making a plane that extends infinitely in these two directions, includes the vectors u and the vector v, and all the vectors in between and outwards. So it's a two-dimensional object that includes these points: the vector v, the vector 0, and the vector u, and of course any linear combination of those. So for what values of h is this vector y with components h, 2, and 4 in the span of u and v? Let's try to figure this out. Well, vectors in the span, this, remember, means vectors that can be written in the form x1u plus x2v for any x1 and x2 in R that are real numbers. So we want to know, what does h have to be so that this vector y can be written like this? Because for this vector equation here to have a solution, it means there is a way to write h24 as a linear combination of x1 and x2. So let's write this as a system of equations and as an augmented matrix and row reduce it and see what happens. So this was just doing the scalar multiplication and vector addition here. And this, just like before, this vector equation is equivalent to the system of 3 different equations where these 3 components are all equal. And we can write that as an augmented matrix 1, 3, 0, 0, 0, 2, h2, 4. And then we can row reduce this. We can do -3 times row 1 plus row 2 to replace row 2. Clear out that 3. That makes the new row 2 -3 times 1 plus 3 is 0. -3 times 0 plus 0 is 0. -3 times h plus 2 is -3h plus 2. And we're leaving row 3 alone. We can continue getting this to be in reduced echelon form by swapping these two rows here, because we want to have the x2 pivot position in row 2. And now we're in echelon form, and we can see where the pivot positions are. Well, maybe this last one is a pivot position. Now, if this is a pivot position, if -3h plus 2 is not 0, then that last equation is in the form 0 equals something non-zero. If it's not a pivot position, then there's no pivot position in the rightmost column, and this does have a solution. So what does h need to be? Well, just a quick solving of this equation. H would have to be 2/3. And that answers the question. Cool. So you can see how pivot positions of augmented matrices is really closely related to questions about, connecting arrows together in R3, this kind of stuff. Now, for part C, we want to know how many solutions does x1u plus x2v equals 0 have? We're still talking about this kind of equation. It's just that we have 0, 0, 0 here now. And we know that this is equivalent to the system of equations with augmented matrix 0, 0, 2, 0, 0, 0. By the same logic we've been doing for the last couple problems. And we can imagine doing the same row operations that we just did in part B here with this and this. It's just that now those row operations have zeros instead. So we can say there are some row operations that are going to reduce this to 1, 0, 0, 0, 2, 0, and in the right, adding multiples of 0 to each other and moving them around keeps them all as 0. So there's the straightforward way to see how many solutions this has by just saying that this says x1 equals 0 and 2x2 equals 0. So that's one solution. Or if you want to get practice applying theorem 1.2, which is a good theorem to be studying and trying to use, we can see that the pivot positions are not in the rightmost column, so it is consistent. It has at least one solution. And is it just one solution or an infinite number of solutions? Well, there are no free variables here because every one of the columns has a pivot, so there's a unique solution. And both of these are great. The second one, you're practicing studying the theorems. The first one is more straightforward. Either's fine. All right, so that was a lot. That was section 1.3. We are deep into vectors. Good luck with the exercises. Some of them might be pretty tricky. But remember, it's always a good idea to work in a place where you can get help. And with that in mind, I'll see you in class. Take care.